Okay, this is lecture 16 already. Yes. So from now on, we will try to calculate the drift diffusion model. So we wanted to get the solution of the drift diffusion model. First of all, we have to talk about what is the drift diffusion model exactly. Yes, so when you say drift diffusion model, we are talking about a set of 5 equations. So a set of 5 equations are called as drift diffusion model. So sometimes people say model or drift diffusion equations or sometimes drift diffusion scheme. There are many different names for this drift diffusion model. So we have to solve these 5 equations. Here you can see that the first one is a Poisson equation. Yes, you know it quite well. Actually, as I told you before repeatedly, its exact name or more accurate name would be Gauss law. However, in vacuum or in homogeneous material, its form can be casted into the Poisson equation. That's the reason why we call it as Poisson equation without much rigor. But anyway, this is the Poisson equation or Gauss law we have to solve. In order to solve this Poisson equation, we need the information about hole density at a given position and hole electron density at a given position. So these two informations are required. For that purpose, we have to solve the continuity equation. If we wanted to know the time derivative of your electron density or your hole density, you have to solve electron continuity equation or hole continuity equation. That is quite understandable. And when we just write down the continuity equations, and we naturally find that the change of electron density is governed by the flux of electrons or flux of holes, and that is closely related with the electron current density J sub n and the hole current density J sub p. So since we know J sub n by solving the drift diffusion equation, after that, when we integrated this J sub n over a certain contact area, then we can find the current of that contact. So of course here we have a minus sign from our convention, and yes, so that is a little annoying, but anyway you can easily understand. Once we understand the current density inside our device, then by just a simple integration over a certain part, we can calculate the contact or terminal current, which is of our ultimate interest. So that situation is easily understood. And if we really understand this situation, then our next question is, what is the exact form of J sub n and J sub p? You know, if we try to understand n and p, then we are transferred to continuity equation and continuity equation. And if we wanted to know n, p, again we are transferred to Jn, Jp. Then what is Jn, Jp? If we say Jn is a function of another physical quantity, then we have to go to that equation, another equation, another equation, another equation. So this is not a closed set of equations. It is open, and we have to go to or visit another equation. So that is quite a tedious and endless job. So in this drift diffusion model, we wanted to finish this hierarchy. So just to say that our J sub n should be a function of our electric field and electron density. So once we close our relation like this, then electric field itself is calculated from Poisson equation, and electron density is calculated by continuity equation. So coupled system of Poisson equation and continuity equation will give us a closed set of equations. That is our strategy, and you have studied that actually this procedure takes a lot of approximations, so it cannot be done without approximation. So after taking all of that approximation, we have arrived at this equation and this equation. This is not an equation exactly, so just a definition or description of J sub n. Once we know electron density and electric field, or hole density and electric field, then our current density vectors like electron current density J sub n or hole current density J sub p can be immediately evaluated. Okay, so anyway, this is 5 equations we will think about in the drift diffusion model. Okay, and I have to say that this drift diffusion equation is actually the model we have to use in the computational microelectronics. So when you solve a drift diffusion equation only, then you don't have to talk much about it, because this is the standard. And if you try to solve additional equations or different equations, then you have to specify, because leaders do not expect other equations as governing equations. Okay, so this is drift diffusion model. Oh, so therefore it is easy to say we have to solve 5 equations. However, you can see that here we have J sub n and J sub p, and actually the expression for J sub n and J sub p is just given here. So by just inserting these relations into our continuity equation, in other words, just combining our continuity equation and the expression for current density, we can merge it and get a merged equation and reduce the total number of equations. So this is 5 equations, but we can reduce it just to 3. So of course, Poisson equation is not changed, but when you go to the electron case, then this is the combined equation. So here you can see this is just a continuity equation, but explicitly we just write down the J sub n. Oh, now since the explicit form of J sub n is used, so we can just solve this one equation to get full information about electronic part here and there. Now you can understand. In principle, we have to solve 5 equations, but in the combined form, we can solve 3 equations: Poisson equation and electron continuity equation. Of course, this electron continuity equation contains the explicit form of the current density and also hole continuity equation. Okay, So these three equations are sufficient closed set of equations. Of course, since we have three equations, then we have to also introduce three unknown variables. These unknown variables are, of course, electrostatic potential and electron density at a given position and hole density at a given position. So now if we have, for example, n points in n mesh points inside our system, then usually in the drift diffusion model, the number of unknown variables is roughly, I can say, 3 times n. Why I'm saying roughly 3 times n? Because in some cases, if your system contains, for example, oxide, insulator resin, then in this case, actually, you don't have to assign electron density or hole density. So the number is not exactly 3 times n, but roughly the number would be like 3 times n. Yes, so I think that all of you have good understanding on this description. And let's go to the steady state case. Steady state case simply means that the time derivative terms are set to be 0. So in this case, our equation becomes greatly simplified. So there is no longer time dependencies. So everything is just time independent. And here you can see this is once again just j sub n, and divergence of j sub n equal to 0. That is the continuity equation we have to solve in the steady state. Okay, so quite easy and straightforward, but practically that is really important, so we have to really careful about dealing with these equations. Okay, today we will talk about n plus n plus structure. This is the test bench for our implementation. This is not my invention. This structure has been used quite a long time to make a comparison between different transport models. So I think that there are many previous works on these structures. So I think that that is really good to have this structure as our test bench. So here we will talk about long structure and short structure. So long structure has 600 nanometer length, and short one is 10 times shorter, so 60 nanometer long version. And the reason why we call it as n plus n plus structure is when we consider this one-dimensional space, the left side and right side, we have a contact. Here we have a contact, and here we have contact. Of course, this is metal and also metal. And inside it, we have 600 nanometer or 60 nanometer long structure. And this is divided into highly doped N plus resin and highly doped N plus resin and lightly doped N resin. Of course, since this part has higher conductivity, also this part has higher conductivity, actually when we make a conduction through this one-dimensional structure, most of its conduction property will be determined by this lowly doped resin. So these and these are just used as contact to the metal layer. So actually this part should be regarded as the active one, where electrons are fast moving and some interesting phenomena can occur. Okay, so anyway, here we have much larger doping density than this lightly doped one. So lightly doped one has order of 10 to the 15 per cubic centimeter. However, highly doped one is about 100 times larger. So in this case, this one is treated as N and N plus, N and plus. But when you go to short version, then in this case we have lightly doped part which has the doping density of 10 to the 17 per cubic centimeter, and N plus has about 100 times higher density. So now you can understand which one is N and which one is N plus really depends on the situation. So that is just a relative measure for the doping density. If you have a higher doping density, then that part takes just N plus, and if you have lower doping density, then that is called as your N. Of course, we have a certain feeling about absolute number also. However, for I just treat it as a relative sense. Okay, so then let's go to the next part. Since we are talking about the solution of a boundary problem, then we have to, of course, specify the boundary values. If we solve the Poisson equation, then we have to specify the electrostatic potential. And if we solve continuity equation, then of course we have to specify electron density or hole density. In this specific case, N plus N and plus structures, so doping densities are quite high. So hole density inside these systems can be quite small. For example, since we have 10 to the 15 per cubic centimeter for this lowly doped, even for lowly doped lesion, so hole density would be just order of 10 to the 5 per cubic centimeter. So there is 10 orders of magnitude difference between electron density and hole density. So this hole density never contributed to any meaningful physical description. So we can just neglect hole density and consider only electron continuity and Poisson equation. And in the Poisson equation, we can safely neglect the contribution from holes. So when we go back to the Poisson equation, in N plus N, N plus structure, we can safely neglect this whole contribution only because the system of our interest contains only N-type regions. Of course, when we have P-type regions, this is not justified. So we have to solve both of electron continuity and hole continuity. When we come back to the boundary condition, then one thing we have to keep in mind is the electron density at boundary in this long device should be 5 times 10 to the 17 per cubic centimeter at these two boundaries, because the doping density at those positions are 5 times 10 to the 17 per cubic centimeter. So since we assume ohmic contact at left boundary and right boundary, so here we have a metal semiconductor, and the position just attached to metal is assumed to be in the local equilibrium. So therefore we have to say electron density. This is the form of electron density. Electron density should be the doping density. Okay, then by using this expression, of course you can calculate the potential, so at equilibrium, and this value is used for the boundary value for your Poisson equation. Already you have done it in the previous lectures, so this is just a reminder for you. And why don't you just consider 60 nanometer long version? So in this case our short version, then our electron density should be now 5 times 10 to the 19, because that is the doping density. So here we have also 19, and you can easily imagine that the electrostatic potential should be a little increased here. Okay. Then first of all, we have to solve nonlinear Poisson equation. Although our ultimate goal is calculate the continuity equation. However, please don't try to solve continuity equation directly, because continuity equation is really heavily affected by the electric field, because inside it, its J contains the terms like Q, mu, n, and E. So this electric field really governs the behavior or motion of our electrons. So without proper description about the electric field, we cannot get any meaningful result out of continuity equation. So first of all, we have to solve nonlinear Poisson equation to get the electric field. Then maybe you can ask me question. Then if our goal is eventually solve the bias like 1 volt, then how can we approach this case? So as we did in the previous lecture, of course we cannot directly jump into this 1 volt case. So if we really wanted to solve the problem at 1 volt, then the overall procedure should be like this. First of all, solve nonlinear Poisson equation. Of course, this nonlinear Poisson equation is strictly valid only at equilibrium. Okay, and this is just equilibrium case. And even for this case, starting from this nonlinear Poisson equation, now you have only information about electrostatic potential. And now at equilibrium, please solve Poisson equation and continuity equations. So this is a drift diffusion model, and when you use your potential calculated from nonlinear Poisson equation as the initial guess for your drift diffusion model, then you will find that actually the solution or the drift diffusion model is immediately satisfied by this electrostatic potential. This is quite obvious because we are talking about equilibrium case, same system by 2 equations, and actually drift diffusion model at equilibrium can be reduced to the nonlinear Poisson equation. Only after we have the full solution at equilibrium case, then we can go to the next boundary condition, like for example v equal to at v equal to 0.1 volt. Still we have to solve drift diffusion equation, and again another drift diffusion equation for higher bias 0.2 volt, 0.3 volt, until we are not arrived at 1.0 volt, the target bias voltage. So today I will show you the procedure up to here. Of course, I'm not talking about the fully coupled Poisson equation and continuity equation. That is task of our next lectures, and I will just show you just solving the Poisson equation and just to solve only continuity equation, and you will find that this continuity equation is automatically satisfied by the solution of our nonlinear Poisson equation. This is the main overview of our lecture structure today. These slides just shows nonlinear Poisson equation solver. So I think that I don't have to repeat this nonlinear Poisson equation solver. You have done it many times in previously, so we can just skip this part. Okay, so just have a look at the lecture material in the GitHub. Then when you solve this nonlinear Poisson equation, then as a solution you will get the electrostatic potential phi, and this phi is written as your position x, and here you have a long device whose length is 600 nanometer, and as I told you before, so this is n plus reason. So here you have n plus reason. Now we have the structure and the solution. This shows just electrostatic potential over position. And in the main body we have lightly doped resin N, and as you can see that we have higher potential and lower potential here. Of course, if we have to estimate the electron density, how can you do that? We can just use N equal to Ni exponential phi over Vt. So by using this expression, which is strictly valid only at equilibrium, and we can find that we will have a lot of electrons here, and we will have a much smaller number of electrons here. One interesting thing is, although our doping density is not like smooth, we have introduced a really abrupt change of electron density. Between n plus reason and n reason, we have more than 100 times difference in the doping density, and its difference occurs abruptly like this. So at this point we had 5 times 10 to the 17, and just nearby we have 5 times 10 to the 15. Yeah. That was the doping density. However, as you can see, instead of that, our electron distribution will show smooth transition between this highly doped region and lowly doped region. So that is one point. So although our doping density is developed, but electron density shows a certain smoothened behavior. So yeah, that is one thing we have to keep in mind. Yeah. So anyway, this is just a repetition of our previous lessons. So we were able to solve this system. So this is nothing new. But now, by using this potential as an initial guess, we will try to solve the continuity equation. So that is the main topic of our today's lecture. So let's go to the continuity equation. So our today's goal is to solve continuity equation. Continuity equation in our combined form is given as this form. Okay. However, we will concentrate on just one-dimensional structure only. So for this one-dimensional structure, so these operators, differential operators, can be just changed into d over dx. So everything becomes quite easy. So in this case, the equation we have to solve is simply given by this one. So you can easily understand this is just a simplified form of divergence, and this is corresponding to our electric field, and this one is also one-dimensional expression of gradient of electron density. So this is just one-dimensional ordinary equation, and we can solve it. So, but here, when you have a look at the equation, I have intentionally introduced a color difference. So, for example, this n or dn over dx, these are highlighted with red color. And here we have electrostatic potential related term d phi over dx, but I just assign the black color, normal conventional color to it. So why? So in this case, I will just consider a situation of fixed potential. So potential itself is given from the nonlinear Poisson equation, and we will just solve electron density only. Of course, this is possible because we have already the exact solution. We have already good electrostatic potential. That's the reason why we can only solve the electron density. But in the more realistic case, more practical case, usually we don't have the well-known electrostatic potential. Then what should we do? In that case, we should consider both of electron density and electrostatic potential as unknown variables. That will be our next task. So in the next lectures, so we will consider this type of approaches. But for a while, as the first day of solving the continuity equation, we will just treat our electrostatic potential as a given number, given profile. Now we have unknown variables, and it's a first derivative, and overall it has the derivation. So this is a second derivative equations, and here we have mobility and diffusion coefficient. So mobility and diffusion coefficient are not unknown variable, but these are material parameters. And actually, this mu n or dn contains a lot of information. For example, this quantity contains the information about electrons' effective mass. Also, it contains some information about relaxation time. Also, this of n have certain information about tau times velocity. That information is related with this diffusion coefficient. So, in general, modeling of mobility and diffusion coefficient are quite complicated. However, we make a bold approximation. That bold approximation is that here we will just treat it as constants. I mean that in usual that should be a function of a position, and dn also should be function of position, but we will say this is constant over position and also constant over position. So mobility in general should be a function of position, but we will consider it as a global constant. And furthermore, we will introduce that relation. So so-called Einstein relation and diffusion coefficient and mobility are proportional, and even the proportional coefficient is well-known thermal voltage. So of course, this Einstein relation is valid only at equilibrium. So equilibrium, this is really true. This is always true at equilibrium. So we can say so. However, point is, we will apply it to even non-equilibrium case. Can we justify this extension? So first of all, if we go to a slightly non-equilibrium case, of course, this relation will hold approximately. Yeah, that is true. However, if we go to strongly non-equilibrium case, obviously we cannot say so. So this is really serious one. However, still we will apply this Einstein relation in our drift diffusion model. So then maybe you feel that, oh, if so, then that means something is really seriously missing. Yeah. So if we go to really highly non-equilibrium state, our physical description now becomes really incorrect. However, even in that case, please note that we are still using it. And amazingly enough, the calculation result out of this simple Einstein relation, which is not valid at highly non-equilibrium case, still give you satisfactory result for your IV characteristics. So that's the reason why they don't feel much motivation to, how can I say, improve the situation. And of course, I have tons of stories, long stories about this treatment, but that will be quite lengthy. And I wanted to just say that there have been many smart guys in this field, and they are quite much educated. So therefore, they try to improve this description. Oh, if we go to highly non-equilibrium case, we can use different dn values. So therefore, we can find many previous works to generalize this relation. However, unfortunately, practically, nobody is actually using the relation beyond this Einstein relation, because practically there is not much difference in the calculated result. So please understand, there is no theoretical, theoretical justification for Einstein relation at non-equilibrium case. This is a serious theoretical drawback. So this is really weak point of our drift diffusion model. However, they are using it. So we will also use this weak point. Maybe you feel a little uncomfortable about the use of Einstein relation, but you know that we have already introduced many approximations, and this is another one. So of course, if you really don't like it, then the best way is just to come back to your original equation. Oh, I cannot stand with these crude approximations. How can I escape and become a more accurate result? In this case, please solve the Boltzmann equation, Boltzmann transport equation exactly. Then you will get the solution. But that is related with significant increase of computational burden. So in an academic sense, you can do it as much as you want. However, in practical sense, it is not very much prepared. So in everyday calculation, more or less, we are living with this approximation. Okay? So then we have only 10 minutes left. Then let's go to the remaining stuff. So since our goal is to solve the system like this, then we just integrate it over certain control area, and the lower bound and upper bound, now you understand their meanings. So this is just a midpoint between xi point and xi minus 1 point. Xi minus 1 point, and this is the midpoint between xi and xi plus 1. So by taking this integration, now you have difference of j sub n evaluated at upper bound and lower bound. And when we evaluate our j sub n at upper bound, you can find that this is corresponding to your drift term, and this is corresponding to your diffusion term. Okay, drift and diffusion. And here we have d sub n. Oh, since we have applied Einstein equation, Einstein relation, then that can be written as Vt thermal voltage times mobility. So this drift term and diffusion term, both of them share the mobility. So we can just pull them out, and now we have drift term and diffusion term. Since mobility is considered as just a constant, so they can be just safely neglected. This one becomes just a multiplication of a constant. So when we are talking about the difference between Jn evaluated at upper point and lower point, or upper bound and lower bound, then we can just calculate the differences between this one evaluated at upper bound and evaluated at lower bound. However, in order to calculate these numbers or these expressions, we have to identify these first derivatives. For example, we have to calculate the first derivatives and first derivative. Fortunately, they can be easily approximated as phi I plus 1 minus phi I divided by delta x. You can easily understand this approximation because we have already used that approximation in previous equations. And also in this case, the n over dx can be approximated as ni plus 1 minus ni divided by delta x. You can get it. And here we have a little complicated term, ni plus half. So we have electron density at xi. We have electron density at xi plus 1. We know it, but we are now asked to provide the electron density at this point. How can you do that? In this lecture, I just suggest you to approximate it as just average of ni plus 1 and ni, so divided by 2. That is my suggestion, naive suggestion about the electron density at midpoint. So maybe you think that why he calls it as a naive approximation. As a student, maybe you feel that it is quite reasonable. Okay, because we know electron density. We know electron density at these two boundary positions, and by applying just a linear variation, we can easily get this midpoint number. Quite easy and straightforward, but later you will find that this is not the case. This makes serious problems, but for a while, just to treat it as linearly varying function, and we will use it. Now our continuity equation now becomes the Jn evaluated at upper point and Jn evaluated at lower point. Their difference becomes 0, and by adopting this discretized form, we will use the calculation. Okay, so then now our discretization scheme is shown here. Please have a look at it. So all the remaining thing is just given here, and also we have previous lecture 15.5, then you can find more information. So actually the implementation is quite straightforward, then you can do it without much difficulties. When we fix the potential as a given profile, then this is linear and this is linear. So in this lecture, we will treat a linear system. So you can just solve it once. This is the reason why we have just only one update here, calculate update, and you will find that if you do it correctly, your residue vector would be quite small. Therefore, your update vector is also quite small. So your electron density as a final result will just similar with your initial guess. So this one shows the solution for short structure. Now you have 60 nanometer, 60 nanometer one, and doping density or electron density is much higher. Okay, so I see that I have to delete this one. This is 10 to the 19, 5 times 10 to the 19. Okay, so now I think that everything is covered, and let's go to homework number 14. So what you have done up to now is just to solve nonlinear Poisson. So you have it already. After that, just to using the fixed potential and electron density calculated from this fixed potential, try to evaluate continuity equation. Then you will find that this continuity equation is automatically satisfied these two solution vectors. My homework today is now consider a p-n junction instead of this n structure. In both regions, P and N, doping density is given by 10 to the 17 per cubic centimeter. And follow the exactly same way. Solve nonlinear Poisson equation. Then you will get electrostatic potential. And from this one, you can reconstruct electron density and hole density. Then try to solve the continuity equations. Then you will find that the update vector is quite small. That will be your homework number 14. Compared with the lecture material in today's lecture, the only complication is related with inclusion of a whole continuity equation. Previously, you have just solved the electron continuity equation, but in this case, you have to solve both of electron continuity and whole continuity. So that will be your challenge. So please try to solve it. Good luck to your homework number 14, and see you next Monday. Bye.